All right, Mr. Schoening here, and what I'd like to show you today is problem number 4 from the worksheet that we were working on in class today. That was the first law of thermodynamics. Now, question 4 is a typical cycle type of problem, and what we mean by a cycle is that we undergo a couple of different processes until we come back to our starting conditions. So what's going to happen in this particular type of problem is that the gas is going to progress through. If we actually look here at the different information, it says here we have some conditions here. All right. And then it expands. So that means it goes to a new condition. And it says now it goes to a temperature of 800.
Josh Kroicke, please contact more.
Then it says that Then it says what we do is we now cool it at a constant volume to this. All right. So then we do that. That's our third thing that we've ended up having happen. And then if we take a look, it says we compress it isobarically to this temperature, to its original volume. And then technically, finally, it comes back to its original state. And the key here is that that original state means that we've completed the cycle. We've come back to the same pressure and volume conditions that we have here. So what we're looking to do is we're going to construct a PV diagram, and then number 2, or letter B, we're going to determine the 3 different things for each of the processes. So there were actually, when this was all said and done, there were 4 things that happened. There was the transition from the blue stuff to the green stuff, then the transition from the green to the yellow, that was transition number 2, and there was a transition from yellow to red, that was transition number 3, but then the red goes back to the blue, and that's the 4th of the transitions. So what we're going to need to do is plot them out as we go. Now, if we're trying to construct the diagram, here's what's actually going on. So what we're doing is we're starting off, normally when you do these types of problems, I'm going to do them actually in the colors that are indicated. So I'm going to start off at blue. So if I'm trying to make it as a graph, what I see here is that it's just starting under some kind of conditions. So I'm going to put it right here just to be safe, right there. And the first thing we see is that it goes through an isobaric change. So isobaric means that it's going to keep the same pressure all the time. And what's going to happen is it expands. That means the volume is going to go up. That means that I have to have a graph that goes something like this, and it angles, or it's pointed in that direction. All right, and it produces a certain amount of work, and then we get the B. So here's where we started off. That was at A. Now we're going to transition over to the green, and now we're here at technically B. We'll make green. The next thing that we see here is that the green goes to a temperature of 800, and now it's going to cool down at a constant volume. So the volume is going to stay the same, but it's going to cool down. Now, cooling down, we saw before on these charts, if we move in this direction, that's indicating higher temperature. So if we went up with a constant volume, we would actually get higher. So we're going to go down here until we get to the yellow state, which will be yellow. All right, so we're now here at spot C. Now I'm down near the origin. I shouldn't be down on the origin, but that's where I roughly am. I forgot to put my arrow on, indicating I'm going that way. Now, if we keep reading, it says, now we're going to compress it till it becomes the red dot back to the original volume isobarically. We said isobaric means that you will keep the same pressure as you do that, but we're going to come back to the same volume value here. So we're going to head here. Oh, sorry, I did the wrong color there. My apologies. That should be yellow. Okay, we're going to be yellow coming into the red. So we're going to go this way. And then finally, the last thing it says we're going to do is we're going to use constant volume to go back to the original state. So this final line here is going to be red. And that's going to go up, and we're going to see something like this. Now, a few things that we can do. Now, we don't have the numbers necessarily to do this right now, but if we wanted to calculate the work, we said the work is the area under the curve. But in this particular case, the area under the curve is actually bounded. So what we actually would do if we're trying to get the area here is we actually color in the shape. So we would actually have to get the area of that shape if that's what we wanted to do. We're going to go about a different approach. But if we had values for these pressures, these volumes, all these values here, we could easily just do the box, and that would give me the work. Now, the sign of the work is dictated by the highest line. So the sign of this would be negative because there's more area under the negative portion than there is under the positive. So remember, going this direction is negative work, and going this way is positive work. So the higher curve always dictates the sign. So this would end up being a negative amount of work if we do that. And we'll kind of just see where that all goes as we do this. All right, so what do we do? Well, if we want to actually calculate these values, we had a lot of numbers thrown in front of us. We need to decipher what's going on here and figure out what's taking place. So state A was in blue. So I'm going to list all of my normal values that I do, and that's going to be my pressure, my volume, my temperature, and my moles. Now we know for all of these, the moles are 1. I'm going to do the same thing for each color, just to keep track of them. I've got B. And what I would do here is, again, I would do my pressure, my volume, my temperature, and my moles. I'm just going to keep repeating this. Unfortunately, we're going to really run out of room very quickly with this, but we got P, V, T, and N. And then we have to basically then get the last one, the red. That's also the P, the V, the N, and the T. Now, what that basically means then is if I start filling these in, oh, sorry, I have my T and the N backwards. Let me fix that so everything's consistent here. That's just so we're on the same order for all this. That doesn't really technically matter. But that's T, and that's N. Now, we know for all of these are all 1. Okay, and then this is also 1. We're going to fill in the values that we know at each spot. So here's what we do next. Okay, we look at the beginning and we see that we have a pressure of 1 atm, converted that's 1 E5. All right, we also know that we had temperature was 400, so I'm good here. So I start off with my values. And what we can see here is that if I use the ideal gas law, I could do PV equals nRT. Using those blue values, I should be able to get that volume without too much difficulty. And I'm not going to solve it out here because we're running out of this video is going to be way too long if I do that. But we can clearly see here that I have the numbers necessary. R is a constant, PV, N, and T are all known. If I calculate out this volume, I will get 0.033 cubic meters. So what do I do with that? Well, I'm going to place that value right here so I don't lose track of it. Oops, sorry, that's too many zeros. All right, so I'm going to also avoid writing units from this point out just because I don't have a lot of room on the board here. All right, so now I know all my conditions about A. I'm ready to go on to B. So let's see, what do I know about B? Well, at B, it says it went to a temperature of 800 K. I see that in the problem. It also says that it did this in an isobaric fashion. That means if it is isobaric, then all I really need to do is use the same pressure that I had before, because that's what it means to be isobaric. It means maintain the same pressure. So I could go over here and I do my PV equals nRT with all the values that I have there, and I can calculate my volume for those who are logical here and don't want to run all the math out. We can actually see that in this equation, the only thing that is different is that the temperature is doubled. So if the temperature is doubled on this side, well, right here, then the volume must double, because it's on the other side and it's a direct relationship there. So I, without doing my math, I'm just going to get 0.066 for my value. So now I know that. So now I go down the line and say, okay, well, let me just keep this process going for the C's. So I go over to the values for the C, and I now see that it's happening at a constant volume. All right, so temperature, it says it goes to 400. That's good. I can fill that in. That was right here. But it says it's going at a constant volume. Well, if the volume's constant, then it must be the same number as the previous step, 0.066. And now all I need to do is just rerun my PV equals nRT again with the values that I have this time. And I'm not going to put them in the calculator, but assuming I did this right earlier, I have 5E5 as my value for my pressure here. And now finally I go over to the red, and I'm going to finish out what I have here. So it says when we are in the red, it goes isobarically. Isobarically means that I got to keep the same pressure. So this will be 5E5. It's going back to its original volume. So I could do one of two things. I can actually go and solve this if I want to, or I could just realize, wait a minute, the original volume was already set. That was 0.033. And then the temperature, looks like it was given at spot D. The original temperature was 200. So actually, I didn't even need to do PV equals nRT to do that one if I didn't want to. So what we've now done is we've figured out all of the values that we needed that we can take over to the next part of this. Because right now, all we did was use the gas laws. The thing that we've got to do now is calculate these values for each particular part. Now I'm going to need to go to the snip tool real quick because I want to carry some of these numbers over. So I'm just going to snip this up real quick. And I'm going to bring the values over, so give me a second here so I can do that. All right, I'm going to copy this. And I'm going to move over to the next slide, and we're going to continue it from here. All right, so I'm going to just paste. And, oh, there we go. Okay. So I just wanted to bring this over so we can continue it and figure out where we're going to go from here. So the next step that we need to do in this type of process is we now need to look at what happened as we transition it. I'm going to do this more as a table, I guess is what we would say here. So we, you know what, I should probably resize this then, make this a lot smaller because I'm going to have difficulty writing this all in here. So I'm going to shrink this up a little bit here so we can do more over here on the side. So what we basically want to do is we're going to be looking at our delta, oops, sorry. We're going to be looking at our delta U, our W, and our Q. Okay, and what we're going to do here is we're going to look at each individual state. So from A to B, how are we going to do that? Well, the delta U, we said, is 3/2 NR delta T is how we would calculate that. Actually, you know what? I'll just write that there the one time, and we're going to put the A to B just a little bit below that. Okay, the Q we've got to figure out, and the W is going to be negative P times delta V. And then the Q will be the difference. So what we'll do is we'll say this equals this. So all we basically need to do now is just put the values in that we have. So for example, this would be 3/2. My number of moles was 1. My R is 8.3, as always. And my temperature change from A to B was from 400 to 800. So I had a positive 400 change. I should be easily able to do my math here, solve that out. I'm going to trust that I had these right, but I'm going to end up with 8.2. I'm sorry. That was the next one. We're going to end up with positive 4980 when we do that. The delta V, or the P delta V that I would do here is I just take my pressure that I was given. The pressure was a constant, 1E5. And then the volume, when we look at the volume here, it changed from 0.003 or 0.033 to 0.066. So that volume expanded to 0.033. And then what I can do is I can get my work, and I see that I get negative 3,300 there for my work when I do that. So basically all I would end up doing then is I just have to calculate the Q. Now what has to happen is that these are supposed to equal. So this Q value that should be here when I do this, and I'm not going to solve all the rest of that because it's going to take me absolutely forever to get all these numbers in for you. But what has to happen is that Q plus negative 3,300 should equal positive 4,980. And that means that if I work that all out, I should have a pretty big positive number. And I believe if I did this right, it would be something like 8,280. So what we see here is that if we put all three of these numbers together here, this plus this would equal this. All right, and that's how we would go about doing that. Now, the rest of the procedure that we need to do, and I'm not going to finish this out just because this video is getting really long at this point, but now I would go from B to C. I do exactly the same procedure because I have my delta T's for all of these. I have my delta V's for all of these. So as long as I can calculate the U and the W with no trouble here, I just simply would calculate the Q as the remaining number that adds up there. All right, so I will finish putting the numbers in for this, but we have 1. We have for the R value, that's 8.3. And then we see that our delta T in this particular case goes from 800 to 400. There's a change of negative 400. And we end up with negative 4980 here. We would do the same thing over here on the P delta V. We would just put our numbers in there and we would go from there. Now, in this particular case, there was no volume change from here to here, from B to C. So that means that this is just flat out 0. And then hopefully we see that this one's nice and easy. Then that must mean that this is negative 4980 because...
Caitlin Armstrong, please contact 4001. Caitlin Armstrong, 4001.
Because the work plus the heat has to equal this. And if that's 0, well then this equals this. And that's basically all you do. So you'll do the same process. You'll do C to D, and then you'll have to repeat from D to A until you come back to where you are. Now, if this is done entirely correctly, we put them all together, because on your diagram, when we drew that little PV diagram over here that looked something like this, that did that, because we're going to end up at that same P and V condition, that means the gas is going to return originally to its state that it was originally in. That means that the temperature should be the same, because according to PV equals nRT, if the P and the V, the N and the R don't change, the T's got to be the same as it was in the very beginning. That means if I do all of my math correct here, that this total, when I put all of these together, should add up to 0. Because when I return, and that's one of the things that is very important to recognize in a cycle, is that at the completion of the cycle, the gas itself should be back to the temperature that it started. Yes, it might have generated some heat. Yes, it probably produced some work. But the temperature of the gas should return back to where it was, because the gas did its job, and now it's back to being what it was in the first place. All right, so hopefully this video was able to help you out a little bit. It's pretty long, but again, a few things to recognize is that when you get a cycle process, just make sure that you just go from one state to the next. You're gonna have to apply the gas law as many times as needed to get through each state. Make sure you pay attention to the hours that you use. And again, the area is dictated by the highest arrow. All right, so that's how we're going to end up working these out. If you have any questions with this, please feel free to see me during our scheduled office hours, and I can continue to explain this one for you. Good luck with the problems the rest of the way.